application. This talk will be delivered by Mr. Prakaski from EduTech. So I request Mr. Prakaski to take over.
Yeah, thank you, team. Thank you, participants. Shall I share my screen?
Please share your screen. Yes, it's visible.
Okay. Thank you. Yeah, thank you for confirmation. So, good afternoon, team. This is Prakash from EduTech India. I'm an manager on emerging technologies and the future mobility labs. So today, our key objective is what is CPS and what is the principles of CPS, the fundamentals, and uh, what types of applications. And these are all the topics we are going to cover. So I give you a short introduction about the core concepts. So year back, people started to talk about the AI, artificial intelligence, and people slowly started to integrate AI and robotics in that industrial field. But this evolution is not started this era. Actually, it's very long back ago. Initially, people who are all manufacturing the things. For example, we can consider the table, normal table. This tables made by the humans through the manpower, and slowly we introduce that uh, energy power, like we are using the steam engines to do this mass productions. Then slowly we integrated the electricity. Once we use the electricity, then IT boom happened. In the IT, we developed computers and the devices, PLC, and we integrated all these devices in that industry. Then finally, this is the era, Industry 4.0, and the 4.0 is nothing, CPS, cyber and the physical system. When we talk about the cyber and physical system, this is Industry Revolution 4.0, where each devices should communicate to each other, or we can say connected devices. One, it will be the edge devices. Maybe I hope you know that different types of layers. When we talk about that industries, the hardware and the software have the multiple layers, starting from the edge layer and the fog and the cloud. For example, in the industries, if you're using some controllers, sensors and actuator, these are all the edge layer, the physical hardware which is available in the industry. On top of that, you need to store the data, you need to process the data in one server. We can consider this as a fog. That means before the cloud, you can collect huge data and you can store it, you can process it in your local machines or maybe the local server in the industry itself. And the selected data can be pushed into the cloud. That is what the final stage, cloud layer. Nowadays, people are familiar with that AWS or that Azure cloud services from Microsoft, and even Google also providing the cloud services. So these are all the cloud where you need to collect the data from the industries, you need to store it, you need to process it. Then again from the cloud you can send back through the fog or directly to the edge devices. That is what the devices to devices or interconnected devices. That means all the controllers can connect it internally, and the cloud and the device can communicate to each other through network. So all devices is just sync to each other. Then when we move to that principles, what are the key concepts, the fundamentals are this 3C. We can say computation. The C, first C is computation. The second is control. Then finally computation. That means think, do, and talk. So if it is an industry who are all using their CPS, the core technology will be this three part. So I'm going to touch two different applications. CPS is not only for the industries. When we talk about that robotics or smart factory, smart mobility, these are all the different types of cyber physical systems are there. Those are all the different applications. So today I'm going to cover two different applications. One is smart manufacturing or the smart industry, and the second one is smart mobility. How we can do the research on this two area. When we talk about the smart factory, that is what the industry 4.0, where I told you, right? It's a cognizant, or we can say interconnected devices, and everything is smart enabled. That means AI will be there in the edge level, and both physical and the cyber, the digital data and the physical devices can sync to each other, and we need to do the real-time data analysis, decision making, and we need to improve the efficiency and productivity with the help of AI. This is all what is happening in industries as a smart industry, we can say. And the second one is smart mobility. People talking about the smart cities where the self-driving car can pick up the person from one point to other point, and they can drop it there. So these are all the different types of smart mobility application. One is outdoor autonomous vehicles, or that indoor mobile robot, warehouse robots. This all comes under that smart mobility topics, where here also you have controls, computation, and the communication, this three C. So I slowly touch up different types of robots, and how you can do the research on this CPS, what are the concepts you can cover it. So first is I told you, right, I am from edutech, and we are also offering the CPS lab, where we will help you to set up the hardware like a mobile robot, or the robotic arm, or the self-driving car, indoor or outdoor, both is possible, and also the drone, aerial autonomous vehicle. So I'm going to touch upon the research with closely with our components, because we're also doing some form of research with some institutes, and we are offering this lab to all IITs, NITs, and the Tier 1 institutes. So first, we cover up the computation part, or we can say think. When we talk about that think or computation, in that first application, smart factory, one key robot in that smart factory is robotic arm. In the robotic arm, we need to do sensing. That means you need the sensors to see the thing and understand the thing, or we can say think. So in this case, in this video, where you can see that the robotic arm and its digital twin, and both the digital twin, the cyber or the digital twin, and the virtual, sorry, the real hardware is synced to each other. That means in all the joints, and the encoders can collect the data and send the data to the cloud. From the cloud, you can receive it in other devices, and you can replicate the same thing in the digital space. And also parallelly in the left side, you can see the robotic arm with the RGBD camera, where you can get RGB color image and the depth image. From there, you need to do the segmentation, which is our object. Where is it? That means in the workspace, what is the location? From the robotic arm, what is the distance? You need to do all this computation. So this is what in the smart factory we are doing the computation part with the robotic arm. So here, this is one example for the pick and drop. One method is a formal method where you can do the image processing, and other method is using deep neural network, so that the basic image processing technique, we need to do all the calculations, and we need to identify the suitable algorithm for different types of samples. In this case, for example, we can consider the label scanning. In this part, if you're using the basic image processing, you need to do the OCR. For that OCR, one thing, you need to train all the letters which format you are using. Then only you are the traditional OCR method is suitable for this application. But in future, suddenly if you change the label, then entirely you need to change the algorithm. But if it is a AI, you can give only 10 or 20 samples, then automatically it can train. So in the future, you no need to change the algorithm. So this time it's a label scanning. Next time I need to do that object segmentation. In this case, one object will be the circle and other object will be the square. So for this again, your OCR is not suitable. You need to change other algorithm to identify that from the color image to the black and white to that edge direction. From that, you need to do some algorithm. Then only it can identify what object it is, whether it's a square or circle. Using the histogram data, you need to do all the calculations manually. But if it is a AI algorithm, the same DNN algorithm can used for different types of samples. Today it's just boxes. Tomorrow it may be the vehicle. It may be the car. For example, you need to fix the nut and bolt in the seat. So the same algorithm can be used. So that's how people are evolving their technology in the industries. Mostly that algorithm will be the similar thing, so that a small configuration is required instead of swapping the entire program. As like previously, previous example is a robotic arm. This time it's a drone. In warehouse, drone is used to do the surveillance and the data logging. It will go to that warehouse storage area and it will scan all the labels. It can pass the data to that cloud, and you can do all in and out activities. You can monitor the in and out through the drone. So for this case, how you can do the research. This is our drone platform, and you are seeing onboard computer. We are offering a indoor drone where it's dedicated for the research. You can do all types of algorithm development for the CPS or that smart mobility. With this NVIDIA, it's powered on NVIDIA Xavier onboard computer. There is no Arduino, it's a direct NVIDIA. NVIDIA with all the sensors, the drone can do the real-time AI computation like this. For example, you can hear that propeller sound, and it is doing that hover. It is just take off from the ground to the TV level, and it is detecting the TV, and it will tell you this is the TV, and this is the backpack. And the left side you can see we are using real-time AI. That means it's not a pre-recorded video. It's a real-time. So the drone will fly parallelly. It can do the AI computing. That is what the power of hardware we are offering to the researchers. So this is one example for that computation for the drone. And the third one, it's like the smart mobility. Previous two option will be like a smart factory. This is example. It's like a smart mobility where you can. I hope you are familiar with that autonomous car or the self-driving car. In the self-driving car, the key applications is like the key features are like emergency brake, cruise controls, or that traffic signboard, signals recognition, and lane keep assist or autonomous driving. So for this case, from the real image, you need to do the segmentation like this in the top. You need to do the segmentation or the lane detection and annotations. So in this case, the same thing, it's also applicable for the research people. So if you are familiar with this concepts, or you need a platform instead of doing the simulations, if you need a platform, we are also offering this platform. That's what the 1/10 car. I will show that the hardware which we used for this videos. I'm just covering the concepts, the CPS, where you can see we are offering the 1/10 car, that is a indoor small size car with the NVIDIA AGX Orion board, inbuilt board with the RGBD camera, 4 CSI camera, IMU, and 2D LiDAR. It's equipped with sensor-rich devices. In the same thing, you can do the segmentation or lane detection using these types of AI algorithm, ULU or the lanelet dedicated AI algorithm to do this types of research. And The same thing if you are doing the research on that controls. Previously, it's a computation. It may be the industry or that smart mobility. I'm going to touch up both controls part. So when we talk about the controls for the robot, it's all about the principles here. The objective is starting from the right bottom imaging. There's nothing from the color image. Color image, you need to do that image acquisition and object detection. From there, you need to move the arm or you need to move the robot. So that's what the fault kinematics, and you need to do the research. This is the arm. Same way you can replace with that bot or the drone. The skeleton is same for that mobile robot and the or the robotic arm. You need to do this joint controls and some path plan. You can execute the particular task like a pickup and drop it in some other location or from one container to the other container. These are the concepts you can cover it. And for the robotic arm, previously robotic or the mobile robot, the previous architecture it's a static. The forward and the joint and inverse kinematic. That this is what the structure. But if it's a drone, it's all about two control. One is stability control and another one is autonomous navigation. For this is example of our drone. We are offering this drone, and it is also sensor rich, where it's a NVIDIA CSI camera and RGBD plus time of flight optical flow sensor and two IMU. By fusing all this together, you can achieve this level of stability. This is one example for that external noises made by human, or even in that MATLAB Simulink, you can simulate your noises like environment. You can use the environmental model to give the disturbance like a wind or other disturbance. You can give that one option. And the right side, you can see that the stability, what level of stability we can achieve. So we are going to do backflip, not only one time. We are going to do triple or four times backflip within 5 seconds. So in this video, you can see this one. So this level of stability, you can achieve it with our solution. And if you're doing research on the controls, the concepts, you can cover it like starting from the basic mathematical model of the devices, and you can do the motor model. From there, you can identify the suitable parameter for the control, and you can change the control algorithm. It may be the feed forward, feedback, or PID, LQR, state feedback control, whatever it may be. You can change algorithm, you can validate it. And also that indoor 1/10 car, where we are, this is what the car, and with a smart map. Here you can see the smart traffic light. It can detect the traffic and it will open up the particular lane. Like if it is a huge traffic on one lane, it will open up that lane and it will close the remaining lane. This is what the smart infrastructure, where all devices, all car can communicate to each other. Each car know what is the current location of the car and the remaining car. Similar to that, traffic light also know all the data. If there is a four car, it know all four car location, nearby four car locations, and it depends on that. It will open up the traffic light. And the right side, you can see the digital twin. And the final part, we already completed the computation controls. Now it's communication. When we talk about the communication, this is one example where industrial robots, warehouse robots, they should navigate to that multiple obstacles, and all the devices should connected internally like a mesh, or either it's a centralized or decentralized. You need to communicate all the data. If there is obstacle, If you're going to apply brake, you need to share this data. What is your current your bot and the remaining bot, like the way you can develop the algorithm for the communication. This is for the mobile robot, and this is for the drone. With our drone, you can do this swarm intelligence, like all four drone can do a single operation with the same trajectory. One video, so that a drone, if there is a problem with one drone, it can send the signal to the remaining drone, and it will safely land the object, and it will go back to the home position, like the way they can internally connected. And also yeah, all this drone. So left side, previously it's a four drone, but right now it's a six drone with a multiple trajectory. It's not like a circle path, it's going up and down. So this, that means it is not manually controlling. All drone are automated. In real time, they can do that computation, they can do controls, and finally they can do the communication. And this is for the architecture. Hmm. At the same time, you can do both manual control, object tracking, and this is how the data communication. Each drone have its own stabilizer with the NVIDIA board, and all the devices connected through the same Wi-Fi network. So from my ground station, my from my laptop, I can pass the waypoint so that all drone can follow my trajectory. Hmm. Similar to the drone or mobile robot, what will happen if we run 10 smart cars? When people are talking about the autonomous truck, where in that industries, the goods transportation happening through this types of truck, that means a 10 truck should follow the particular direction, and it will pick up the object and it will drop it somewhere in the industries, or it may travel through 100 kilometers, 200 kilometers, and with a limited control enabled truck, it's making that human activity and less or comfortable, so that he can stay calm and he can monitor the system. And the just 2 more minutes. This is what our offering edutech, we are offering this smart factory example. We are offering that mobile robot and robotic arm and drone for the smart factory, where you can see our drone and the mobile robot, they can communicate to each other like heterogeneous. It can do the master follower. So right on the right, you can see landing and takeoff from the moving robot. And the same way, robotic arm can also sync to each other. That means, not similar to the drone, you can communicate your current position of the bot to the robotic arm, and you can see the robotic arm is sending the data. Whenever the bot receives the data from the arm, then it will change light. Right now, the LED color is purple. So whenever the robotic arm changes its states, the robotic bot will acknowledge that. So it's like a master slave. Bot will send the signal, robotic arm will acknowledge, then bot will respond. Like the way you can do that smart factory application, or you can use our digital twin and the robotic arm for that smart mobility. We are offering that, yes, indoor car. So this is what that car look like. I will quickly go through the research. Segmentation, instead of on the real car you're doing these things, it require multiple you need to follow multiple rules and regulation. But if you're doing research on indoor, you can simply simulate this in the lab itself with our indoor car. You can do all the type of research, and later you can use the same model with some level of tuning with the real car. So that's all. This is what we're offering for that research. And this is not only in India, it's happening across various countries. We are working with multiple countries, and this few of equipments from West academic people, how they are doing research. From University, Northeastern University, where they are doing our indoor car with that cyber physical network analysis and design, and they are doing that applications like cloud-based systems, smart energy system, autonomous vehicle, biological network, and a few more academic from Canada. So these all the outcomes from thing. You can do research, you can do the publications, and also you can achieve the conference. This is the paper you can see. Uh, Using our small indoor car, you can replicate that the scenario like a four-way junction without traffic light. It is very difficult to emulate in the real world using four car and four lane. It is easily can replicate in the indoor with a one-tenth car with the four-way junction. How your AI algorithm will navigate to this dynamic scenario. You can develop your research and you can publish it like this. By this, I stop this presentation. You can go through this products what we are offering. If any doubt or anything you need to reach me, I'm sharing my mail ID here so that you can reach me. You can share your doubt in future.
Thank you, Mr. Prakash, for delivering talk in this GAM course. So I request participants, if you have any doubt, please ask.